do have a couple homework questions I didn't get to on WebAssign. So I do plan on addressing those also. So if you feel like you need a little bit more work with this homework, I will spend a little bit more time on it today. My only real agenda is finishing 4-4 today. Other than that, I'm not super concerned about starting 4-6, whether we get there or not. Not a big deal to me. Honestly, it's probably best that we don't. Just kind of stick to this. Okay. So I was doing number 22 on 4-3, and everyone should have had the same iteration for this problem. We're in the interval from negative pi to pi. So we took the derivative, set it equal to 0. And I was saying that in class we had done a similar problem to this, but there wasn't a 2 on it. So our problem that we did in class was like sine theta equals negative cosine theta. And when we solved this equation, we were just trying to think about places where sine and cosine had the same absolute value, but opposite signs. This is slightly different because you have this coefficient on the 2. And due to the coefficient on the 2, you kind of have to solve this using a different method, because we don't actually have any special trig angles where the value of the cosine is twice the value of the sine or vice versa. I mean, we have root 3 over 2.5, but that's not like a double situation. Root 2 over 2, and then of course 0 and 1. So we went ahead and divided both sides by cosine just to get this into one trig function, which was tangent. And then we said that tangent theta equals -0.5. And then we went ahead and said, okay, fine, we don't know of any exact angles where we would have the tangent value be plus or minus 0.5 even. So we went ahead and just said, okay, theta must be the inverse tangent of -0.5. And by definition of the inverse tangent, when it's negative, your calculator and just the definition of it automatically will pump that into quadrant 4 between negative pi over 2 and 0. And I demonstrated that by just saying, okay, well, inverse tangent, -0.5, and then this is negative 0.4636, which is between 0 and negative pi over 2. So that's that quadrant 4 angle as you work your way down here. Because of course, negative pi over 2 is approximately equal to negative 1.57. So if this is negative 1.57, this spot right here would be right about negative 0.4636. So that's kind of where this came from. So inverse tangent -0.5 would be over here. And the interval that we were looking at was from negative pi to pi. So then we were thinking, okay, we're going to need one more place where this happens, or at least we're going to look for it. And remember that with tangents, you're always going to have the same, signs on them if you work through the pole. That only works for tangent and cotangent. But you can also just consider the fact that tangent is going to be negative in quadrant 4, and tangent is going to be negative in quadrant 2. Tangent is positive in quadrants 1 and 3. All students take calc. The T is for tangent, cotangent. So that means it's positive in 1 and 3, negative in quadrant 4 and 2. So in order to get to quadrant 2, to get to that polar opposite, we added pi. So we took this angle that we had that was in quadrant 4, added pi to it, and got this quadrant 2 angle, which, I mean, if you need an approximate, that's fine, just to eyeball it, but my math lab, WebAssign won't accept an approximate anyway, but it's about 2.68-ish. So that's right here. And of course, pi is 3.14-ish. So you can kind of see how that works. So these are the two critical numbers, and you won't be able to find any outside of here. If we're only looking in the interval from negative pi to pi, well, it's gonna happen once over here in quadrant 4 and once in quadrant 2. It's not gonna happen from negative pi to negative pi over 2 because tangent, is positive in this interval. And it's not gonna happen from 0 to pi over 2 because, again, tangent's positive in this interval. Before I do part B, which was asking about, sorry, I totally lost it now. Let me go back and get it. think it was asking about min and max values. It was asking about, yeah, local mins and maxes. So before I do part B, does anyone have a question on part A? All right. So part B is asking about local min and max values. So we have critical numbers, and these are places where on the graph, these values of theta would be giving us mins and maxes. So what you're going to do then to get the actual min and max values is you're going to go back to your original function. I'm going to rewrite it here because it's not going to fit. I'm going to look at the note that was attached to this. Okay. Because I know at least 2 people asked me about this one. I'm looking to see if anyone else asked me, see what they mentioned on it. See anything. Okay, so here's your function value. Go ahead and evaluate these values at your inverse tangent. So you're going to look first at theta equals inverse tangent negative a half. Oh, I see where I'm seeing now where all the confusion lies. You did this in trig, but you probably don't remember it. When you do this, you're going to first take f of the inverse tangent of negative a half, and you're going to get sine inverse tangent negative a half minus 2 cosine inverse tangent negative a half. Now, you're going to have to evaluate these 2 functions. So go ahead and make yourself a triangle. Okay, technically it should not be a quadrant 1 triangle. Let me make this. I'll pick a different quadrant. It really doesn't matter, but it's going to drive me crazy. I'm going to make it a quadrant 4 triangle. Okay, so there's your theta. Now, remember that for your inverse tangent function, when you have inverse tangent of negative 1/2, that really means that tangent theta equals negative a half. That's the equivalent notation for what you're doing here. Now, if this is your angle theta, remember that your tangent of theta is the opposite over the adjacent. If I can jog your memory here, I know it seems like such a basic trig thing, but you probably haven't thought about these functions in a while regarding triangles. So the tangent of theta would be the opposite over the adjacent. So you'd have negative 1 over 2. And if you weren't sure which one to put where, I mean, we're going to be able to fix the sign in a few minutes anyway, the SIGN. But that's kind of why I made this a quadrant 4 triangle, was just because I know that in quadrant 4, I'm going to be going down, which is negative, and then over, which is positive. So this is kind of what your triangle would look like in that case. And then you would just be missing your hypotenuse. So you have negative 1 over 2. So negative 1 would be the opposite. 2 would be the adjacent. So there's your tangent theta. And then in order to get the hypotenuse, let me see, c squared equals a squared plus b squared. Use the Pythagorean theorem. Negative 1 squared plus 2 squared. And you'll get c squared is 1 plus 4, which means c squared is 5, and c is the square root of 5. It's the hypotenuse, so we're just going to let it be the positive version of this. If you have questions, stop me. You did do this in trig. You just might not remember it. All right, so as far as evaluating our function now, we have a triangle that is set up to represent inverse tangent -1/2. And now we need to find the sine of this angle. So remember that when you're saying inverse tangent -1/2, what you're looking for is theta. So we can consider this to be some angle theta. I mean, it's equivalent to saying tan theta equals -1/2, but the inverse tangent itself is an angle. So what we're looking for now is the sine of this angle. And the sine, remember, is the opposite over the hypotenuse. I'm running out of like side space here. Sine theta is the opposite over the hypotenuse. And of course, cosine theta is the adjacent over the hypotenuse. So the sine of our angle is -1 over the square root of 5, because we're looking at our angle theta and we're taking the opposite over the hypotenuse. And then when we evaluate the cosine of the angle, well, the cosine is the adjacent over the hypotenuse. So the adjacent is 2, and the hypotenuse is the square root of 5. So you have -1 over the square root of 5 minus 4 over the square root of 5, which leaves you with -5 over the square root of 5, which is probably fine, but you can rationalize it by multiplying through by the square root of 5, and then you'll just get negative square root 5 in that case, because these two together give you 5, and that will cancel out with that 5. So this is going to end up being one of your values. We're going to label it in a second. But before I continue here, does anyone have a question? I know this is kind of branching out a little bit, but it's such a good reminder of these trig things that you used to do. All right, so similarly, since we already know the value of the sine and the cosine, we can find the function value at our next angle. We don't have to make another triangle, though. We know that the sine and cosine values are going to have the same absolute values. We just need to adjust that to be in quadrant 2. So these were in quadrant 4, where we had sine being negative and cosine being positive. That's what happens in quadrant 4. It's going to be the opposite in quadrant 2. In quadrant 2, the sine is positive and the cosine is negative. So you can draw a new triangle if you want to, but you don't have to. In the new triangle, you just would have had a quadrant 2 triangle where the 2 is negative and the 1 was positive. But it doesn't matter, because all you need to do is use the same values, use the same absolute values you had from before, and then just adjust the signs for being in quadrant 2. So sine is positive, cosine is negative. And then you'll have 1 over square root 5 plus 4 over square root 5, 5 over square root 5. Rationalize it. These guys will all cancel, and that leaves you with the square root of 5. You were being asked here, oh gosh, I lost it again. I think it was just for the mins and maxes. I keep having to go back and find it. Use the first derivative test to find any local extrema. Oh man. So technically we should have done like test points using the first derivative test. Well, we know their values now. I guess that's kind of what I was focusing on. But the first derivative test would give you this chart that we came up with, well, that I did for you in the video, where you pick a test value and you use an interval. This kind of leads us into what we have to do today anyway. You evaluate the derivative at the test point, and then you get the sign of f prime. And you make a conclusion. So our first interval would go from negative pi up to our first critical number. And the first critical number would be the smaller one, which is the inverse tangent of -1/2. And then you would go from that critical number to the next one, which is inverse tangent -1/2 plus pi. And then you would go from that critical number to your right endpoint. And we did get approximates for these. Maybe I did not write them down. They were about -0.46. So you have an idea where you're pulling from, and about 2.68. So maybe for the first interval, you would want to test something like -1. Maybe for the second interval, you're going between about -1/2 and 2.68, so maybe +1. And then between 2.68 and pi, I would probably just choose 3. And then evaluate your derivative at those values. Your derivative was cosine theta plus 2 sine theta. You might just want to put this into your calculator. You certainly don't have to. But I think that's going to be the fastest way to do this. So your y equals is cosine theta. Remember, we're looking at the sine of f prime, not f. We're not looking at function values here. So f prime is cosine theta, and then minus or plus 2 sine theta. And then you can go to your table and then look at what's happening at -1, +1, and 3. And all we really need to know is, I mean, all I really care about is the value, but I do want to know that you actually popped this into your calculator and checked it out. So -1.143 is negative. 2.2232 is positive, and -0.708 is negative. So that will give you some indication as to what your critical numbers are actually representing. So up until you get to the first critical number, your values are decreasing. Then in the second interval, I know it's a long interval, but this is one interval, your values are increasing, and then they start to go back down again in the third interval. But this matches the function values that we found. We just sort of did this in reverse. You would have had to have gone through and found these values anyway. Your function values here are going to be -√5, which makes sense because it's a smaller value and it's a minimum. And then at inverse tangent -1/2 plus pi, you had +√5. So your first derivative test is this table that we did down here, and it showed that you had intervals that were decreasing and then increasing at this one critical number, and then increasing and then decreasing at the next critical number. And then when you actually evaluate the function, your original function at these values, you come up with the mins and maxes. There was a lot involved in that one. The first derivative test itself, I don't think was the hard part. It was actually just coming up with these function values. And maybe you would have evaluated the function at these values in your calculator. You would have gotten approximates, but you wouldn't have gotten the square root of 5, for instance, if you would have just evaluated the sine of the inverse tangent, for instance. I mean, you can check it in your calculator. Sine inverse tangent -1/2 minus 2 cosine inverse tangent -1/2. You'll come up with this value, which is actually, sorry, wrong button, the negative square root of 5. But you wouldn't have known that unless you would have actually gotten through your triangle, because you would have just said, okay, well, I don't know what this value is, and you would have approximated it, and the answer would not have been correct. So that's that one in a nutshell. So yeah, you know, it just goes to show anytime we start to really get into these equations and such, especially when it involves trig, just the strength of your prerequisite knowledge really starts to become more and more important here, as far as being able to solve different types of equations involving rational exponents and radicals and trig functions. Just so many of the things that you kind of learned leading up to this point are all being used now to solve these calculus problems. This is part of the office hour notes, so I will be posting this along with the rest of the office hour notes. I don't know what happened to the other page. It's somewhere, but I will be posting it. So weird. Maybe it's under here. There it is. I'll be posting it on D2L. So I also did 4-2 number 10 and 4-2 number 12. So I'll post that also so that you can peruse them. Let's see, I can't answer every single question, but I did get, okay. I did get some questions about some of these exponential functions, so maybe I'll do something like that real quick. Kind of see what's, pick through here and see what's left from the questions. I do need to get through 4-4, just only 4-4, but still I need some time for that. So this one is uh, 4-3-4-4, number 15. The function should be the same for everybody, x e to the x. And you're being asked here to determine intervals where the function's increasing and where it's decreasing. And I think sometimes with these different types of functions, we need a little bit more practice. It seemed like I wasn't getting as many questions about like polynomials, for instance, or even rational functions. It was more trig functions and exponentials and logarithms. There was one, I'm going to see if I can find it real quick, that I got a couple different people asking me about. If we're looking for areas where our function is, or intervals where our function is increasing or decreasing, we're going to go ahead and take the derivative. So f prime g plus f g prime, and we're going to set it equal to 0. To do that, and to solve this equation, factor out your e to the x, and then use the zero factor property to solve. You're going to get used to seeing e to the x equals 0. When you see that, just remember that your exponential function is never going to be equal to 0. It's not going to happen. You can't take this to any exponent and get it to be equal to 0. So also, you know, that e to the x graph looks like this. It has a horizontal asymptote at 0. So your function can't take on that value. But that you could get x equals -1. And the domain of your exponential function is all real numbers. You don't have any exponential limits here on what you can use as your variable. So x equals -1 would be your critical number. And I'm glad we're actually going over this because I want to make sure that we are kind of getting used to setting up these intervals. We're going to set up intervals on either side of the critical number. We don't have any domain restrictions for the exponential or for this polynomial. So we can go ahead and start our intervals at -infinity and take that up to the critical number at -1. And then take our critical number at -1 all the way up to +infinity. Go back to this question. Okay. Go ahead, Morgan. What's your question?
So I did -infinity to -1, and then I did -0. Would that be wrong?
Wait, then you said you took it up to 0?
And then I did like 0 to infinity.
Oh,
yeah,
well,
like I did -1 to 0.
Okay.
And
yeah,
then 0 to infinity.
Yeah, because that implies that 0 is a critical number, even though technically in your test intervals, you would still get the same result in both intervals. You'd be chopping it off at 0, which you don't want to do because 0 is not actually a critical number. So because 0 is not a critical number, don't include it. You can use it as a test point, which I am going to do, but it shouldn't be an endpoint to one of your intervals. Does that make sense?
Yeah, so why isn't 0 a critical number in this case?
Well, because our critical numbers are only going to be values that make the derivative equal 0, and 0 doesn't do that. E to the 0 is 1, and then if x is 0 in this term, you just get 0. So f prime of 0 is e to the 0 plus 0 e to the 0, which is 1, plus 0, which is 1. So f prime of 0 doesn't give you 0. That's why it's not a critical number. And since it's not a critical number, it doesn't go in your intervals. Does that explain it a little bit better?
Yeah, it does.
Okay. Okay, good. I'm glad you asked. Let's see, I'm just going to pick another test point. Any other questions here? The actual question I got on WebAssign was about what to do with this piece. Like when you use the zero factor property and you factor out the e to the x, what do you do here? I think I answered that. If you still have a question about it, let me know. But e to the x can never equal 0. So you just kind of exclude that equation from your result. Okay. So now we're going to use your test point and evaluate the derivative there and then make a conclusion about where your function's increasing or decreasing. So go ahead and look at your derivative. If you want, you can plug this into your y equals. I'm not going to just because it's, I don't know. First of all, e to the x is going to be positive regardless of what x ends up being. So I don't need to worry too much about that. But I am just going to use my derivative, and I'm just going to say e to the -2 times, plus, not times, plus -2 e to the -2. I mean, it's the same as doing your calculator table. So if you feel more comfortable with doing that, that's fine. But you're going to get approximately -0.135. So the sign of your derivative's negative. And then I'll just do the same thing at 0, which I actually already put up here. No, wrong one. Now I have to get rid of all these negatives. Gosh, it would have been faster to just retype it. 0 times e to the 0. So that's f of 0, which is 1, which is positive. And it's a critical number, so we are expecting that we probably will get a sign change here. It won't always happen, but because it did, we know that it's going down, it's going up, because we had a minus and a plus. So that must mean that our critical number gives us a local minimum. Your question was just asking about intervals on which it was increasing or decreasing. However, it wasn't asking about mins or maxes. So you would just say that it was decreasing on negative infinity to -1 and increasing on -1 to infinity. Oh man, I'm looking at your WebAssign answer and I don't think they're going to enforce it, but for some bizarre reason, I forgot that they do this. They use square brackets instead of parentheses. Ugh. Maybe you didn't see that at all. Maybe it's just popping up like that in my solution. It's always going to be parentheses because you can't be increasing or decreasing at the critical number. So if they accepted this with square brackets on your test, I'm not accepting that as okay. And you'd lose a point for having the wrong brackets. It has to be parentheses. You are not increasing or decreasing at the critical number. It only happens on either side of the critical number. At the critical number, your function is constant. I don't know why they do that. Okay. Let me know if you have questions there. I'm going to pop this into answered. And then there was one more that I saw a few times that I figure I might as well just go over. And then anything I didn't have time to answer in class, I'll send a response back on WebAssign. So this was number 6 on 4344. I saw this one more than once pop up in my inbox this weekend. It was f of x equals the natural log of the square root of x on the interval from 1 to e, and it was a three-parter. A, verify the function satisfies the conditions of the mean value theorem. Here we go. So we're looking first to verify these 3 conditions, or not 3 conditions. For the mean value theorem, we're mostly just looking for this to be continuous and differentiable on the interval. It's a natural log function. As long as you are taking the natural log of a positive quantity, then we would know that this function is continuous. So as long as x was, as long as x is greater than 0, you'd be okay here. So we would say that f of x is continuous. Yes, because your natural log function would be defined for all of these values. You don't have any values in your denominator where you'd be dividing by 0, and we're not including in the interval any values that would make your natural log function not exist. As far as the derivative is concerned, if you want to go ahead and find the derivative, first I'll rewrite the original function. The natural log of x to the 1/2 is 1/2 natural log x. By the way, on the test, I had a question on there, and I can't remember exactly what it was, but it was something like the square root of the natural log of x, something sort of like that. This is natural log x quantity to the 1/2, which is not equal to this. So it wasn't exactly this, it was something else. There might have been something else under there, like maybe it was natural log x plus 1, something like that. But this is that entire quantity to the 1/2 power, which is not the same. You can't use the power rule because the power isn't only being applied to the x, it's being applied to the entire natural log. So not the same thing here. In this case, the natural log is not under the radical, it's just the x. So you can rewrite it, and that makes your derivative easier to work with because that gives you 1/2 times 1 over x, which is 1 over 2x. Now, f prime of x exists for x not equal to 0, and 0 is not in your interval, so we would say that f is differentiable on the open interval from 1 to e, yes. So those are the conditions of the mean value theorem. The way that you were asked this, I can't really see the way it was given to you, but it looks like you just had to give a yes or no. Oh, no, maybe you had to type it out. Crazy. Oh, so rudimentary. Okay, but yes, we would say it's continuous on the closed interval, differentiable on the open interval. And then part B, find the numbers guaranteed by the mean value theorem. This seemed like a place where people were getting stuck. So when you're using the mean value theorem, remember you're not taking the derivative and setting it equal to 0. You're taking the derivative and setting it equal to the slope of the secant line from A to B, which in our case is from 1 to E. So what you're looking for here for B is f of E minus f of 1 divided by E minus 1. And this will give you the slope of the secant line from 1 to E. F of E is the natural log of E to the 1/2. And you know what? If you even would prefer, use F the way we rewrote it. I know sometimes it's a little sketchy using anything that you've rewritten because you never know if you accidentally rewrote it wrong. But it's not wrong, I guarantee you. It might be easier for you to use this variation. So 1/2 ln E minus 1/2 ln 1 divided by E minus 1. And then you're just going to have to get used to working with natural logs and exponentials. ln E is 1, and ln 1 is 0. You can always enter these in your calculator. If you enter ln E, you're just entering the natural log of E to the first, but natural log of 1 is 0. So this is 1/2 minus 0, because it's 1/2 times 0, and then E minus 1. So we would say that the slope is 1 divided by twice E minus 1. And then it seemed like some people had this or something really close to it. I saw an instance where maybe the subtraction was reversed. I'm not sure how that happened, but I did see that. And then, let's see, for part B, oh yeah, we were still finding the number C that guarantee the mean value theorem. So we are going to set our derivative, which was 1 over 2x, equal to 1 over 2 times E minus 1. And if I were you, I would leave this factored, because when you cross multiply, you get 2 times E minus 1 quantity equals 2x. And then you can divide both sides by 2. And when you divide both sides by 2, you get x equals E minus 1. So your answer for part B was C equals E minus 1. And then part C was just asking you to interpret. And your answer is that f prime of C and your slope are the same. So it's like, since f prime of C is 1 over twice E minus 1, and the slope, they wrote it out fully, is 1 over twice E minus 1. So we just found both of these quantities. Then the lines are parallel. Something like that in short form. Okay. Sorry, I just moved my window in a weird spot. I need to get it back. There we go. Okay. And you know that f prime of C is this quantity because we just found that that was where these two were equal. Okay. Questions on that one? Okay, the other two questions I have not addressed. I will get back to that person individually. It looks like more mean value theorem. Okay. Wonderful. So, sounds like we had a rough weekend and maybe had a hard time with the homework, but we're hanging in there. Does anyone have anything to add to that? I'm going to set this aside so I can add it to our office hour notes. And we'll post after class. Okay, so I had mentioned that chapter 4 is going to be your most challenging, and there's just a lot going on in chapter 4, and we're not even going to get to cover the whole thing. So if I can remind you of my plan. Today I'm going to get through 4.4. I think we'll still have time. I did start it the other day. Today I just need to do the concavity portion. And then we're off tomorrow. On Wednesday, I'm going to be doing some examples from 4.6, which is curve sketching. I could spend an entire 4 days just doing curve sketching problems. There are just so many different types of examples. And I think the more you see, the better you'll get. That's why I do try to include a lot of them. But I'm going to do that Wednesday. And then on Thursday, I'm going to do some word problems for optimization. Students usually don't have too hard of a time with this. I guess technically we could do optimization Wednesday and then just focus on curve sketching. But I thought it might be good to kind of get your feet wet with the curve sketching and then kind of shift gears into optimization. And then for the async, I just wanted to sort of finish out more curve sketching. Do we have a quiz Wednesday or just Thursday? Just Thursday. Yeah, so Thursday we'll have a quiz that'll be covering 4.4 and then 4.6, whatever I cover from 4.6. So your async over the weekend, I figure I'll just do some more curve sketching. So your async, I just don't want to do your asynchronous material to be just completely new right before a test, because your test is Monday, which is the 19th. So for your asynchronous work, I was just going to do more 4.6. So I want you to see it, start working on it, get to feel comfortable with it, talk about some 4.7 and with optimization, and then for your async work, I just wanted to do more curve sketching with different types of functions. So usually I start out doing rational functions, and then I kind of move into polynomials and radicals. Not as many polynomials and radicals, because those functions are just, they don't have as many types. When you're dealing with rational functions, you have a lot of asymptotes and things that change the behavior of the function very drastically. So that's sort of my plan for the week. And then your test 4 is Monday, which is the 19th. So I guess mostly I wanted you to see some curve sketching in case you had some questions on it, and then you could do it in your async work. It's possible that I might think about this more tonight and decide to switch these two. If I do, I have a worksheet that I usually go through for optimization, just because it's word problems and it takes a long time to write all those examples out as I'm going through them. So I will post, or I'll probably just email you the worksheet that I was going to go through. If you don't have a printer, no big deal. You might want to take some time ahead of class just to write out the problems, because some of them are just wordier. But if you do have a printer, you can print them out and just bring that with you to class for the day that we do optimization. Yeah, maybe I'll just do it Wednesday and just end with curve sketching. Maybe we'll do that. I'm going to put some more thought into it. I've actually put a lot of thought into this, but I just can't make up my mind. So we might switch that. But either way, your test 4 is going to be Monday, the 19th, and then move forward into 4.8, which is the beginning of chapter 5, even though it's in chapter 4, and then kind of go from there, kind of pick and choose what we're going to do out of chapter 5. I usually only cover a couple sections. And then it'll be test 5 and final. It'll be over before you know it. And for some of you, that's too soon. Questions on the plan? All right. Moving forward. You know, we're starting to get very tired. I can tell just by the emails I've been getting from people. We're getting tired. Okay. Let's continue talking about 4.4. Let's see if I can remember what this 4.4 is called. I believe it's called low flow streamline concavity. Yeah. I kind of already introduced this, but I would just say concavity because technically I already covered most of the local extrema portion of this when we kind of mixed it in with that discussion of intervals. However, there is a piece of a local extrema that we're going to talk about today with respect to the second derivative. So we're going to talk about that. So we talked about increasing and decreasing functions last week or over the weekend, whenever you did your asynchronous work. Now we're sort of going to relate this to concavity. So I'm going to give you a definition for concave up, concave down, and we're going to use this same process with the second derivative that we did previously with the first derivative. So we're going to let f be a continuous function on the closed interval from a to b. And differentiable on the open interval from a to b. F is, oh gosh, I didn't preface this. Definition, concave up, concave down. Sorry, I said it, didn't write it. F is concave up on the open interval from a to b. If the graph of f lies above each of its tangent lines throughout the interval. Personally, I think that you guys are going to eyeball concave up, concave down. You're not going to be thinking about it and how it relates to this definition, but officially that is the definition for concavity. Sometimes I do have students who struggle to see concavity, so I'm going to show you what concave up looks like. First of all, I'm going to tell you what my Calc 1 teacher told me, which was that concave up looks like a cup. It could hold some liquid in it. Now, that's not always going to be as straightforward. Sometimes you might have concave up where it might only look like half of a cup, and it might be a little bit harder to see that. But the basic definition of concave up is a graph that looks like this. So concave up is like cup. You could put a handle on it like a mug and drink from it. Sorry if it looks like an ear. That's what concave up looks like. If you want to think about it and how it relates to its tangent lines, the graph of f on a graph that's concave up is going to lie above its tangent lines. So if you were to draw the tangent lines anywhere at any point on this graph, you would get tangent lines that look kind of like this, or maybe like that, or maybe like that. And notice that in each instance, the graph lies above the tangent line. So the tangent line kind of hits, and then the rest of the line lies below your curve. So this is the definition of concave up. And we're going to now talk about concave down, but it's basically the same idea with the opposite situation. So F is concave down. On the open interval from A to B, if the graph of F lies below each of its tangent lines. On the open interval from A to B. I don't know if this is a thing, but I once had a student say concave down, frown. Okay. So if you want to think about concave down looking like a frown, that's fine. Okay. Like I said, this is not always going to be as straightforward, but this is a basic graph of what a function would look like if it were to be concave down. As far as its tangent lines are concerned, the graph lies below the tangent lines. You can start to graph them wherever you see fit, and you would see that this curve would lie below the tangent lines. So that's a basic definition of concavity. We're going to be looking at lots of pictures of this. So you're going to see some examples. We're going to have a test for concavity in the same way that we had a test for whether or not your function was increasing or decreasing. And then we're going to talk about kind of relating this back to not necessarily critical numbers, but something that is like that for an interval that cuts off your concavity. So first of all, I'm going to give you a theorem, which is for the test for concavity. We're going to let f be continuous on the closed interval from A to B. Suppose both f prime and f double prime exist on the open interval from A to B. All right, so your test for concavity is going to use the second derivative. Your test for increasing and decreasing used the first derivative. For concavity, we're using the second. If f double prime of x is positive on the open interval from A to B, then f is concave up on the interval. And notice here I'm giving you open intervals. You cannot possibly be concave up at that point where you switch from up to down. So these must be open intervals. Just like how you can't possibly be increasing or decreasing at a critical number. Same idea. If f double prime of x is less than 0 or negative on the open interval, then f is concave down on the interval. Sorry, that looks really weird now. So you might be wondering, like, okay, cool, got it, but how do I find the endpoints of the interval? Like, how do I know where A and B are? Well, those are called inflection points, and I'm going to give you a definition for them right now. Yes, no, this way. Definition. Inflection point. Suppose f is differentiable in the open interval from a to b containing c. If the concavity of f changes at c, f of c, then c f of c is an inflection point of f. So I always think of inflection points as being like critical numbers for concavity. So we get a critical number by taking the first derivative and setting it equal to 0. We get an inflection point by taking the second derivative and setting it equal to 0, or where the second derivative does not exist. And then that's the last theorem I have for you, is sort of just being able to define where to find the inflection point. So now you know what an inflection point is. What an inflection point looks like, by the way, might not always be super clear, but I don't know, let's say we have a graph. It might be something like this, where you have this curve that kind of swings down. Notice that at some point on your curve, the left-hand side of the curve, your graph is kind of cup-like it could possibly hold some liquid in it. And you would notice that your tangent lines would lie below the curve. At some point, the inflection changes, and this becomes concave down. And at some point, you get to this position where now your tangent lines lie above the curve, and there's no way that you could hold liquid in this cup. It would just fall onto the floor. So an inflection point would be where that shifts. And like I said, sometimes it can be hard to eyeball, and students have a harder time seeing this, obviously, than in a situation where you have a minimum or a maximum. We can very clearly with our eyeball see where like a minimum is, because we see that bottom of the hill where we start to swing back up again, or a maximum at the top. And a pointer inflection is a little bit harder to see. I always abbreviate these POI because nobody wants to write out point of inflection, like ever. But this would be a place where our concavity would change from concave up to concave down. And what we're going to be doing here is we're going to be using the next theorem to find places where the point of inflection exists. But the point of inflection would be that switch where the concavity changes. So the last theorem I have for you is a condition for an inflection point. So you'll know how to find one. No, I just noticed there's a blue dot on the chat. Oh, you know what I saw when she asked the question. Never mind, everything's fine. A condition for an inflection point. Let f be differentiable on the open interval from A to B containing C. If C f of C is an inflection point of f, then either f double prime of C equals 0, or f double prime of C does not exist. Okay, now one thing I want to point out, it's very subtle in the definition, but it states here that we're going to let f be differentiable on A to B containing C. So that means that your interval must contain the value C controlling the inflection point. So that means that in an instance where we have, for instance, a vertical asymptote at C, we wouldn't call that a point of inflection because even though the concavity might change on both sides of a vertical asymptote, our function wouldn't actually contain that, like a point CF of C. It couldn't possibly be because it doesn't actually exist on the function. So we still need to consider the fact that the concavity could change over a vertical asymptote, and we're going to see this happen, but we're not going to actually call it a point of inflection. All right, so I'm going to give you some examples now where we are going to determine intervals on which f is concave up or concave down and find the points of inflection. Before I do that, are there any questions here? All right, so example, technically this will be example 1. I don't remember how I labeled this last time for my notes. Probably doesn't matter, you can just write example, but a little bit pedantic over here. Yeah, I think I was like on an example and then I segued and I included this part in example 4. Okay, so this will technically be example 1. Determine the intervals on which f is concave up or concave down and find the points of inflection. And I'm going to start out with a polynomial function. It's always easiest to start out with a polynomial for something like this. X to the 4th minus 8x cubed plus 18x squared. Now, we're looking here for the second derivative when we're talking about concavity. On the test, you will have questions where everything's going to get combined together, but that's going to be your curve sketching problem. Otherwise, I'm going to give you questions asking about increasing or decreasing, and then questions asking about concavity. The reason I do that is because let's say that you get the first derivative wrong. I don't want everything after that to be wrong. I at least would like to give you a chance to actually show me that you know something about concavity. I mean, technically your first derivative could still be wrong, but I don't want all your points lying within one problem where something went wrong at the beginning. So I try to give you multiple examples to kind of show me what you know. First, you will take the first derivative because you cannot get to the second derivative without taking the first derivative. You get 4x cubed minus 24x squared plus 36x. And then you'll take the second derivative. 12x squared minus 48x plus 36. Now, in order for us to have a point of inflection, it must be the case that either f double prime of c equals 0 or doesn't exist. So just like what we did with our first derivative test, looking for extrema, we're going to set this equal to 0, looking for points of inflection. So don't worry about your first derivative. We used it to get the second derivative, but now it's done. We used it. We don't need it anymore. And we can go ahead now and solve this equation. If I were you, I would factor out the GCF first. It's going to make your life a lot easier than having to use all those common factors and try to factor it that way. It'd be a big mess. So the two numbers that multiply to 3 and add to -4 are -1 and -3. So you end up getting x equals 1 and x equals 3. Now, we're not actually going to call these points of inflection yet. We need to actually show that the concavity changes on each side of these. So right now, we're just going to consider them possible points of inflection. Remember that when I wrote the definition for inflection points, it says to be an inflection point, the concavity has to change at the point. So occasionally you will have these values that come out of the second derivative where you set it equal to 0, and the concavity doesn't change. It will happen sometimes, not very often, especially with a polynomial. But I don't label them until I'm sure. So what we're going to do here is we're going to set up a chart just like we did with increasing and decreasing functions to look at the concavity. Now, if you would like, I'm going to add a piece to the charts. We're going to need it for curve sketching anyway. So I think it might be a good habit to get into. We don't really need it to talk about intervals where your function's increasing or decreasing. But when we set up our intervals, let's go ahead and kind of include the piece where our possible point of inflection is, just so we can actually have it in the chart. So we're going to cover our whole domain here, and it's a polynomial function. So the domain goes from negative to positive infinity. And we're going to stop at our first possible point of inflection. And what I mean by adding a piece to the chart is that I'm just going to talk about what happens here at 1 in this case. You don't have to, but you might find that it's helpful as we head into talking about curve sketching on Wednesday or maybe Thursday. We'll see. Oh, not 1 to infinity, 1 to 3. I just realized that the squeaky noise that I, for some reason, kept thinking was my daughter getting upset was the dog's squeaky toy. Ay, ay, ay. It was very disorienting. It's like, wow, she's really worked up down there. Squeaky toy. Okay, I'm still going to pick a test point. The only difference is that in this case, when I set up my intervals and use a test point, I'm not going to evaluate the first derivative at the test point. I'm going to evaluate the second derivative at the test point. Because remember that in order to be a point of inflection, I'm looking for places where my second derivative would be less than 0 or greater than 0. Looking for that now in my definitions, and that must have been further back. Oh, yes. Here it is. Test for concavity. If f double prime of x is positive, then f is concave up. If it's negative on the interval, then we are concave down. And then we'll make a conclusion, or you can say sine of f prime, of double prime, sorry, whatever you decide to do there. So your test points might be 0, maybe 2, maybe 4. I know those are so predictable, but why not? And then we're going to evaluate the second derivative at the test points. Now, if you'd like, if you trust the work that you did, your life is going to be a lot easier if you use the factored version of your second derivative. In a case like this, you don't have to. You can always plug these into your calculator and do it that way. But the reason this is going to be easier is because I can just evaluate the second derivative by saying, okay, I have 12. 0 minus 3 is negative 3. 0 minus 1 is negative 1. Well, that gives me negative times a negative is positive. Just show me some work. I don't need an exact value, but at least show me you did something. If you did it in your calculator table, just give me whatever decimal value you obtained. But you can do the same thing for 2. You can say, all right, well, I have 12. 2 minus 3 is negative 1. 2 minus 1 is positive 1. A negative times 2 positives stays negative. I want you to be able to think a little bit smarter here without having to feel like it's just all plug and chug. And then for 4, well, 4 minus 3 is 1. 4 minus 1 is 3. 3 positives, multiply them together, and you're going to get a positive. So we can say that on the interval from negative infinity to 1, our function is concave up, and from 3 to infinity, it's concave up, and from 1 to 3, it's concave down. I don't care if you write out concave down or C down, or if you write concave up or C up, as long as I can read what you're writing. If you start doing CU and CD, and I can't tell the difference between your U's and your D's, then you have a problem. C up and C down, come on, that's already abbreviated. I think you should be good with that. I feel like I've been talking a lot without answering any questions. Want to make sure I give you an opportunity to ask them. I'm going to summarize this in a second, but do we have questions here? Okay. Wonderful. So our function is concave up on negative infinity to 1 and 3 to infinity. It is concave down on 1 to 3. We can also verify this in our graphing calculator. So we'll look at that in a few minutes and see if we can tell. Sometimes with these polynomials, especially if they have really large coefficients, it can be kind of hard to tell. But we'll see if we can get a good idea of what's going on. You're also going to be asked for the points of inflection, and those are going to occur at x equals 1 and x equals 3, because notice that your concavity went from up to down and from down to up. So the concavity changed on both sides. So both of these would represent x values for your points of inflection. So your points of inflection would be at 1, f of 1, and 3, f of 3. Remember here, we're looking at the actual function value and not the value for the second derivative when we're actually trying to find the point on the graph. So go back to your original function to get f of 1, 1 to the 4th is 1, minus 8 is -7, plus 18 is 11. So you definitely have a point of inflection at 111. And then 3, f of 3 I have down as 27. You can double check that. And now that I'm looking at the points of inflection, I can kind of get an idea, if I was going to check this on my calculator, of where I would need to look to see this graphically. So let's go ahead and put this in our calculators, and you can let me know if you have questions. I'm going to enter the original function, graph it. I just want to show you the points of inflection so that you can kind of see what they look like. This is x to the 4th minus 8x cubed plus 18x squared. Now, if I graph this in Zoom Standard, you're not going to see much. You're probably just going to see a bunch of what looks like vertical lines. Yeah, and you don't even really see that anything is happening over here at what would be 327. So we know that we're looking to see these points at 111 and 327. So like I said, the points of inflection are kind of hard to eyeball, because if you're looking at this and thinking, well, 111, I'm really close to that right now. I mean, really, I could adjust my window by 1, and you wouldn't know that there's an inflection point like right here, because it's not this obvious min or max situation. But let's try to get into a good window. I'm going to take my window, and I'm going to have to adjust this a little bit. I'm going to set my x min to -1, maybe. And I don't need a very large x max, because really beyond 3, nothing's happening. So maybe I'll send my x max just over to 5. Kind of spread this out a little bit. But I'm going to have to lift my graph up. I don't need it to be super low, though. So maybe my y min will be -1. And my y max maybe will be 30, because I know I need to include the point 327. This is just an idea for what I think will maybe look nice, and we'll adjust it if needed. Graph it. Okay. Yeah, so I think this is pretty good. I might even raise the y max a little bit more and lower the y min. Or I'm sorry, raise the y min, raise the y max. So maybe even take the y max up to 35 and do a y min of 0, because there's nothing happening below the x-axis. So maybe that will give you a better indication. So my window was x min -1, x max 5, y min 0, y max 35, in case you were following along. And then we get a pretty good view of what's happening, just on a different scale. And now you can really eyeball this graph and get a better idea of where these inflection points are occurring. So 111, well, remember we have this set out to an x max of 5. So 1 is right here, and 111 is going to be this point, about 1/3 of the way up on your graph. It always looks different on my right in front of me versus on this screen, so make sure I look at it here. This right here is an inflection point. It's approximately 111. And like I said, it's hard to eyeball, but you can see now that you know where it is, that when you look to the left of 111, hold it with this hand, like that. When you look to the left, you're seeing this behavior where you have it cup-like, where you actually have a situation where you could hold liquid in a cup on the left-hand side of that first inflection point. So we did have the graph being concave up on that interval from -infinity to 1. We also had concave up from 3 to infinity. So again, we have, let's see, 1, 2, 3. So right here, would be the other inflection point where our graph changes to be concave up. But until you get to this point, it's concave down. So from 111, what's better here? From 111 all the way up to the next inflection point at approximately 3 or at exactly 327, the graph is concave down. So you can see that in this little segment right here, you would not be able to hold liquid in a cup at all. You don't have a cup. You would just have it spilling all over the floor. And this is a situation where you're concave down. If you want to think about it in terms of the tangent lines, all the tangent lines here would be above your curve. And then there's a switch that happens here at 3. So once you hit 3, now you have some cup behavior again. And now it's only half of a cup, but it doesn't matter. What you care about is the fact that it's curved upwards and the tangent lines are below the graph again. And that change happens right about here. So like I said, it's a little bit harder to eyeball these, but I think once you get the results, you can start to see the way they work, and then they become a little bit more obvious to you, where you're looking for that switch in the curvature of your graph. Does anybody have a question about the result we obtained or the graph?
So did we basically confirm that the possible POIs were actual POIs?
Oh, yes, they're actual POIs. So yes, I labeled them here, but yes, technically you're right. They are no longer just possible because the concavity actually did change on both sides of each one. They are actual points of inflection.
So when there's a change, it automatically switches to being actual points?
Yes, yes.
Okay, thank you.
You're welcome. Yes, thank you for clarifying and going back to that. Other questions here? So basically, I just wanted to do this same thing with a couple different types of functions, just that I felt like algebraically, and I'm glad that I included them because I was asked about some functions like this on the homework. So I wanted to just do a couple more examples using some different kinds of functions. One of them was a radical function. We can talk about concavity. F of x is x times the square root of x plus 1. Now, I want you to get very used to listing out domains anytime you have a function that might have an issue with its domain. So in the last example, we had a polynomial function. Well, we don't really get too concerned with polynomial functions about their domains. Because their domains are all real numbers. But it's going to make a big difference to us if we're looking at a rational function or a radical function, because in those cases, we're going to have restricted domains, or even a natural log function. That's another big one, where we don't want to end up setting up intervals from negative infinity to positive infinity and erroneously including values that shouldn't be there. That happens to students a lot because they don't consider the domain in advance. That's why every semester I'm trying to make a bigger deal about it, just because it keeps happening all the time. So let's discuss the domain of the function. It's a polynomial times a radical, and it's restricted by the more restrictive function, which is the radical. So we need for x plus 1 to be greater than or equal to 0. Because we need the radicand to be greater than or equal to 0. So we would say that x has to be greater than or equal to -1. So when we set up our intervals, we're not going to start at negative infinity because I can't include values all the way down to negative infinity. My domain is going to start at -1. So when I set up my intervals, I'm going to have to start here and work my way upwards. So don't go all the way down and then try to test a value like -5, and then you'll be like, why isn't this working? I'm getting an error. I don't understand what's happening. Make sure you're starting at values that are actually in your domain. Let's go ahead and take the derivative. In order to do that, you might want to rewrite your function to include a rational exponent. This will be x times the quantity, x plus 1 to the 1/2 power. And we'll use the product rule here along with the chain rule. The product rule because we're multiplying two different types of functions together, or we're multiplying any two functions of x together, and the chain rule because we have a composite function for the second factor. So f prime g, f prime is 1, g is x plus 1 to the half, plus f, and then g prime is where we're going to use the chain rule, 1/2 times x plus 1 to the negative half. You don't have to chain on the derivative of the inside function if it's 1, because you don't have to write it, but I'm just showing you because I think it's good practice. F prime g plus f g prime. I always go over these in my head one more time before I solidify them, because sometimes when there's so much going on with your derivative, some things get lost, or maybe you'll forget to chain on something. Who knows? Since we're going to be since we're going to be taking the second derivative, let's go ahead and just simplify the first derivative a little bit here. There's not much to do for the first term. For the second term, I would leave this with a rational exponent. And I would just say this is 1/2 x times x plus 1 to the negative half. We didn't really change much there, but at least it looks a little bit better as far as taking our second derivative. So now when we use f double prime, or when we take f double prime, for the first term, we're going to use the chain rule. And for the second term, we're going to need the product rule and the chain rule. So for the first term, we'll have 1/2 times x plus 1 to the negative half. If you chain on the 1, that's fine. You don't have to show it. For the second term, we're going to use the product rule. So f will be 1/2 x. G will be x plus 1 to the negative half. F prime g plus f. And then g prime is where we're going to use the chain rule. So bring down your half, rewrite the x plus 1, decrease the exponent by another 1. If you multiply by the derivative of the inside function, you're multiplying by 1. And then we'll go through and simplify this and get it set up nicely, because remember, in order to have an inflection point, we need our second derivative to either not exist or equal 0. So I'm going to have to do a little bit of work with this. And I'm trying to be really consistent here with getting these into one fraction so that we're always looking at the numerator equals 0 and the denominator equals 0. And then you don't have to worry about using different solving techniques depending on what your function is. It'll be the same process all the time. But that's up to you, but that's the way I'm going to show it. So if you have other ways of solving this and you get it correct and show me your work, that's fine. I'm just going to be consistent about the way I show it. Are there questions on the second derivative before we simplify it out? So I'm going to rewrite this as 1 over twice the square root of x plus 1 plus 1 over twice the square root of x plus 1. And then minus, because I have a negative here, I'm going to have an x in the numerator. The 2 times 2 in the denominator gives me 4. And then I'm going to use that trick where if I have the 3/2 power, I'm going to write it once and a half. And I'm going to remind you, recall that x to the 3/2 equals x times the square root of x. And I'm just going to apply that here to the quantity x plus 1. So it's negative, so I'm moving it into the denominator and it becomes positive. 3/2 is just 1 and a half. And there are your 2/2. I'm going to combine this all into one fraction next. Before I do that, are there any questions? So your LCD is going to be 4 times x plus 1 times the square root of x plus 1. Now, if you're wondering, like, did I have to do this? Why did she do it this way? Well, because I think if you left it in the denominator as x plus 1 to the positive 3/2 power, I think you'd have a hard time looking at this and seeing what your LCD was supposed to be. And then you'd kind of be stuck on the solving process. I think as long as you can write this so that it has one of these factors in it, that helps you to see more clearly what's missing from these two. So it's not that you have to do it that way, but I think it's the best way to go about it. A lot of times it's just rewriting something in a form that makes it look more obvious to you. So here's our LCD. I'm going to multiply each term by a quantity that will get me to this LCD. The first term already has a 2 and the square root of x plus 1. If I want to get it to be this LCD, then I need to also multiply it by another 2 and an x plus 1. So here's the original fraction, 1 over twice the square root of x plus 1. And we're multiplying it now by what we need to make the LCD. So we need it to be a 4. That's where the extra 2 comes from. And we need it to have a factor of x plus 1. What we multiply by in the numerator, we must also multiply by in the denominator. Technically, you could have just combined these two terms together first. I did not, but whatever. It's 6 of one, half a dozen of the other. Okay, and then your last term already has the LCD. So I have 2x plus 2 plus 2x plus 2 minus x. Now every single term has my LCD. Two x plus 2x is 4x, minus 1 is 3x. And then 2 plus 2 gets you to 4. And there's f double prime simplified into one fraction so that you can take the numerator and set it equal to 0 and take the denominator and set it equal to 0. Before I find possible points of inflection, are there any questions here? Wonderful. All right, so I'm going to go through now and find those possible points of inflection by taking f double prime and setting it equal to 0. Well, that one is pretty straightforward. 3x plus 4 equals 0. (3x) equals -4 and x equals -4/3. And then you're going to go back and ask yourself, is -4/3 a possibility for us? Not just because it's negative, but I mean, that's one thing that might trigger you thinking like, wait a second, I have radicals and I have a negative. Let's just double check. So you go back to your domain and you notice that x has to be greater than or equal to -1. Well, -4/3 is less than -1. So this value is not in the domain. So it cannot be a possible point of inflection. So we just did a lot of work for nothing. Lots of work with very few rewards in calculus. But when you do get the rewards, they're totally worth it. Totally. Go ahead, Morgan. What's your question?
I don't know if I'm doing this wrong, but when I typed in -4/3 in my calculator, I got -1.3.
Yes, -1.3 is less than -1. Yes.
Oh, yeah. Okay.
Yes, so it's
Never mind.
not in the domain.
Yeah.
Yeah.
I see it now.
All right, any other questions there? Okay. Wonderful. Let's look at the denominator. I'm looking for values such that f double prime of x does not exist. And that's going to happen when my denominator equals 0. If you would like, it would be most beneficial to you at this point to put it back in its 3/2 notation. I really like this example because it really just gives you lots of algebraic practice working with these radicals. And solving these equations and kind of working back and forth between the notation. It's very good for you. Anytime I say something is good for you, I hope that doesn't make you feel concerned. Divide both sides by 4. You'll get 0. Now, remember, when you're trying to solve an equation with a rational exponent, I mean, this one you might feel the eyeball. I'm going to rewrite this so that you can see what I'm doing. But you want to get rid of the exponent on here. Not entirely. You want the exponent to be 1. Remember to do that, you raise it to the reciprocal power. And if you raise it to the reciprocal, remember you take a power to a power, you multiply the powers. Well, 3/2 times 2/3 gives you 1. And then you get x equals -1. Okay, well, I have some more bad news for you. This is not in your open interval. Remember that for points of inflection, we are looking for them to be inside the open interval from A to B, whatever that might be. In our case, we're looking at our domain, and we're trying to figure out if this value is in there. This is an endpoint. We said that our domain went from -1 to +infinity. Right there. -1's an endpoint. An endpoint can't be a point of inflection because I would need to have concavity on both sides of the point of inflection. Well, the graph doesn't exist to the left of -1. So it can't possibly be that the concavity changes if the graph doesn't even exist on one side. So in this case, we actually don't have any points of inflection. And you might find that to be great. You might find it to be sad because you did a lot of work and you didn't find any, and that's always a little bit disappointing. But I guess not finding any could be a good thing because it means you don't have as many intervals to look at. I asked you to find intervals on which the function was concave up or concave down. That includes finding points of inflection, but a point of inflection represents a change in concavity. We're understanding now that the concavity is not going to change, but that doesn't mean there's no concavity at all. The function's either going to be concave up on its entire domain or concave down on its entire domain. Oh gosh, f must be concave up or concave down on its entire domain. Hold on, I have a 2-year-old trying to bust in. I don't know where her father is. Hold Sorry about that. Clearly I need hired help around here. Okay. There is concavity. We just need to determine what it is. It's going to be the same thing all the time. It's not going to change. So in order to figure that out, we're just going to pick a test point anywhere on the domain, anywhere you want. And we're going to set up a teeny tiny table. So that we can figure out whether the function is concave up or concave down on its entire interval for the rest of its life. And you might want to pick the test point 0 because it's always easy to work with. And then you're going to look back and try to figure out where your second derivative is. I found mine up here. 3x plus 4. So 3 times 0 plus 4. The numerator will be 4. The denominator will be 1 times 4, also 4, which is 1. And the sign of f double prime will then be positive. That must mean that f is concave up on its entire domain. Technically, the domain includes -1, but obviously you can't be concave up or down at an endpoint. So it's a little bit tricky to say there. So maybe I'll say f is concave up on, we'll just simplify this a little bit, -1 to infinity. Do that. Because technically we can't be concave up or down at an endpoint. Doesn't make any sense. I feel like we should do a natural log function real quick and call it a day. So that one, there wasn't a lot to really conclude there. I just thought it was really great practice for you to work with these algebra techniques that you're going to need throughout this section. All right, the last one we'll do is f of x equals -x squared ln x remember, we need to talk about the domain, and we're restricted by the most restrictive function here. X squared is a polynomial. Its domain's all real numbers. But the natural log of x is only defined for positive numbers, not including 0. So any values of x that are inside this natural log have to be positive. So we're going to look at a domain from 0 to infinity, not including 0. And then we're going to take a derivative, and then we're going to take a second derivative. And find some possible points of inflection. We're going to use the product rule here. So f prime will be f prime g plus f g prime. And then we'll simplify that. -2x natural log x minus x. And then take your second derivative. I would not factor out the x if I were you, because you're going to need the product rule either way. I would just use the product rule again. This time, your functions would be f and g, -2x, and natural log x. So f prime g plus f g prime, and then the derivative of x is 1. And then we'll simplify. So the x's will cancel in the second term, and you'll just get -2, and then you'll subtract 1. And your second derivative is -2 natural log x minus 3. Now, one of the nice things here is you don't have to do a whole ton of work with your second derivative like you do anytime you have a rational function or an issue where you have a variable in the denominator. This one's going to be a little bit more straightforward because we're just going to be able to take f double prime of x and set it equal to 0 and solve. But this is why I kind of wanted to do this problem, just because I feel like working with these types of functions isn't as familiar to us as, for instance, polynomial functions or even rational functions. So I wanted to make sure we talked about how to solve this equation. So add 3 on both sides and divide by -2 because you want to isolate the natural log of x. Now remember, when you're trying to solve a log equation, specifically a natural log equation, you want to raise the base, you want to raise both sides such that the base is e. Because I know that e to the natural log of x is x. So that's like a recall situation. That's a property that you should have learned in algebra. If you don't remember it, I'm reminding you now. It's the same way that if you have the natural log of e to the x, it's also x. Same idea, they're inverse functions. So depending on whether you're trying to solve an exponential or you're trying to solve a natural log, you can use those two identities. And then you have x equals e to the -3/2. Now, we already talked about the fact that your exponential function e is not going to be negative. E to the x is going to be positive all the time, no matter what x is. So in this case, we don't have to worry about this quantity being negative and not being included in the domain. It is in our domain, so we can use it as a critical number. And again, if you're not sure, we're going to need to approximate it anyway, so we can pick some test values that are appropriate. Put it in your calculator as e to the -3/2. You get approximately 0.2231-ish. Now, I always want to see exact answers, but like I said, for your intervals, when you're picking test points, you're going to need an approximate to base that off of. So we're going to start our intervals at 0, not at -infinity. We can only include values in the domain. And we're going to take that up to our possible point of inflection at e to the -3/2. If you want to actually put that into your table, that's up to you. I'm going to put it in there because we're going to be using it later, not later today, but in later lessons. And we can go ahead and find a function value for it and put it in there too. So this is approximately 0.2231. So it's up to you what value you want to test. You can pick a decimal value or you can pick a fractional value. Don't pick 0 because it's an endpoint, but maybe like 1/10 or something. 0.2, just anything that's smaller than 0.22. So maybe 0.10, something. Just pick a test point. And then over here, anything bigger than 0.22 is fair game, or bigger than 0.223 something. So maybe 1 would be a good idea. And then you'll evaluate the second derivative at your test point. Your second derivative is -2 ln x minus 3. And you can see now that 1 was a really good point to choose here because this one's going to be easy to evaluate. The natural log of 1 is 0. So the answer here will just be -3, which means the sign of f double prime is negative. And you're going to be concave down on that interval. And then for the other one, pop it into your calculator. It's probably going to be positive. -2 ln 0.1 minus 3 is approximately 1.605-ish. So it's positive and you are concave up on that interval. So you're going to be asked about intervals on which your function is concave up or concave down. So we know it's concave up from 0 to e to the -3/2. We know it's concave down from e to the -3/2 to infinity. Your point of inflection is going to occur at CF of C. So e to the -3/2 and then f of e to the -3/2. And you're going to have to come up with an exact value here. So go ahead and find f of e to the -3/2. I'm going to put mine off to the, put it off to the side over here, I guess. Put it right here. F of e to the -3/2 is equal to, going back to my original function here, negative x squared times the natural log of x. So evaluating my original function here, the natural log of e to the -3/2 is just going to be e. It's just going to be -3/2. The e is going to go away. When you take a power to a power, you multiply the exponents. -3/2 times 2 is going to be -3. So you have negative e to the -3rd power. And a negative times a negative gives you a positive. So you have 3/2 e to the -3rd, or you could write that as 3 over 2e cubed. Up to you. So when I write this down here in my point of inflection, I'm going to write it as e to the -3/2 and then 3/2 e to the -3rd. So remember, you will have to enter exact values. So make sure you get some practice doing this algebra work. I know it seems silly to say, but make sure that you understand how to actually evaluate these functions here. All right, I'm going to put up some homework. You have a quiz Thursday, not Wednesday, so don't worry about that. But I'll put up some homework on the rest of 4.4. So you'll have to look at finding intervals on which your function is concave up or concave down and finding those points of inflection. So your concavity changed here at the point, your point of inflection. So we would say that that is definitely a point of inflection there. I think that's all I have to say, right? Did I forget anything? I don't think so. If you have questions, let me know. I'll be expecting your emails. I do have some that I have to get to still. If I haven't gotten back to your email from this afternoon, I will address it. I think my husband is leaving in like 5 minutes, but I will address it at some point here, probably this evening, since I have napped. But have a wonderful evening, and I'll see you guys Wednesday.
Thank you. You too.
Thank you.